in this auspicious. Good evening. A warm welcome to all this auspicious evening. Let us start the workshop with the word of Tirukkural. ஒருமைக்கண் தான் கற்ற கல்வி ஒருவருக்கு எளிமையும் ஏமாப்பு உடைத்து, which means the man whose store of learning gains in one through the 7 worlds bliss attains. This 15 days event is a small celebration to learn new and small things we have taken towards spreading knowledge to others in analytical tools for image processing. Prayer purifies our mind and takes away negativity and boosts our energy. It starts with the Tamil Thai Varthu.
நீராறும் கடலொடுத்த நிலமடைந்த கெழிலொழுகும் சீராறும் வதனமென
திகழ் வரத கண்டமிதில்
தெக்கணமும் அதிர் சிறந்த திராவிடனல் திருநாடும் தக்க சிறு பிறை நுதலும் தரித்தனரும் திலகமுமே அத்திலக வாசனை போல்
அனைத்துலகமும் இன்பமுற
புகழ் மணக்க
இருந்த பெரும் தமிழனங்கே சீரிழமை திறம் வியந்து செயல் மறந்து வாழ்த்துதுமே வாழ்த்துதுமே வாழ்த்துதுமே.
Thank you, MPhil scholars and Sid Mohammed sir, for making a peaceful environment with the melody. Life is a traveling to the edge of knowledge, then a leap is taken. I am glad to introduce Pillar of Knowledge, one of the principal investigator of this workshop, Professor Dr. P.L. Chitra ma'am, to deliver the welcome address and introduce our resource person of the day.
Happy evening. Warm welcome to one and all present here for the virtual RUSA 2.0 sponsored 2 weeks workshop on the analytical tools for image processing under nanoinformatics, role of NanoHub in cancer imaging, orthodontics and orthopedic schema and system design, to be held from February 1st to 17th, 2022 at 4 p.m. to 5:30 p.m. in virtual mode. I am very delighted to welcome the virtual August gathering of RUSA 2.0, 2 weeks workshop on analytical tools for image processing. It is my great privilege to welcome our Honorable Vice Chancellor, beloved Vice Chancellor, Dr. S. Gauri. Welcome, sir. It gives me an immense pleasure to welcome our dynamic registrar, Professor Dr. N. Madhivanan, and overall RUSA 2.0 coordinator for this project. It is my pleasure to welcome our biomaterials team 2, ever supporting coordinator, Dr. E. Murugan, Professor in Department of Physical Chemistry. Privileged to welcome the captain of the ship, Dr. S. Balakumar, for ever encouraging and motivating to conduct this workshap. He is the backbone of this workshop. I am happy to introduce, I am very happy to welcome our dynamic chief guest of today's evening, Dr. Santosh, Clinical Lead, Nuclear Medicine, Dr. Ella Institute of Medical Center, Cropet. He has readily accepted our invitation and he is going to be our chief guest of the today's evening. Along with, he will deliver a talk. Welcome, sir. Thank you very much for your time, support to us. Thank you so much. And welcome once again for this wonderful evening. and our participants are ready to hear your words, sir.
Yes.
Welcome, sir.
So, is my voice audible, ma'am?
Yeah. I am happy to welcome. It is my inbound duty to welcome our Professor and Head, Department of Computer Science, Dr. B. Thangaved, and my colleague, Dr. S. Gopinathan. It is indeed a great privilege to welcome my colleagues and the PIs of this project, Dr. M. Swarnam, Professor, Department of Computer Science, Dr. B. Lavanya, Associate Professor, Department of Computer Science. It is a great pleasure to welcome all the faculty members, professors from our own University of Madras and other universities, government college teachers and affiliated colleges from all over India and Tamil Nadu for having joined this program. Thank you very much for your presence, and I am happy to welcome our young and dynamic participants of PG students, research scholars from various departments from computer science, nanoinformatics, bioinformatics, biochemistry, for get this input from our workshop. The aim of this program, I would like to introduce certain things about the workshop. This program aims at disseminating knowledge on recent trends in prediction, medical image processing, deep learning concepts, linear algebra, with case studies with respect to cancer imaging, orthodynamics and orthopedics. Our resource persons are highly reputed, eminent professors, industry persons from national and international level. So this particular RUSA 2.0 project workshop is completely free registration, with certificates will be provided for all the participants, those who are consistently attending throughout the program and taking up the online test on February 7th. தொட்டனை தூரும் மணற்கேணி கற்றனை தூரும் மாந்தர்க்கு அறிவு. தோண்ட தோண்ட ஊற்று நீர் கிடைப்பது போல் தொடர்ந்து படிக்க படிக்க அறிவு பெருகிக் கொண்டே இருக்கும் என்று நமது திருவள்ளுவர் கூறியுள்ளார். அதற்கு ஏற்ப we are just having our workshop which will help all the participants with pouring knowledge throughout all the 15 days. I request all the participants to be alert, make use of this golden opportunity to learn the knowledge throughout. We have our own eminent speakers from industry and research organizations and academicians from national and international reputed institutions. Throughout all the 15 days, they will handle the session with real-time use cases. This is an eye-opener for all the research scholars and PG students to start your career in this domain. Make use of this opportunity. The outcome of this program is to provide domain knowledge, explain processing techniques, hands-on use cases, thereby to upgrade and incline the young minds to research. Once again, I welcome one and all present here. It gives me an immense pleasure again to introduce our chief guest, Dr. S. Santosh, working as a clinical lead, nuclear medicine, Dr. Ella Institute and Medical Center from Krompet, Chennai. We have an eminent resource person with us today. He has fully trained in the preparation, dosing, and dispensing of the radiopharmaceuticals. He has undergone special training in endocrinology, PGIM-ER for management of thyroid patients. He has undergone special training in interpretation of planar dynamic SPECT-CT scans, interpretation of PET-CT imaging, traces, radionuclides, radionuclide therapy, and he has done 3 months clinical rotation in the Department of Radio Diagnosis, PGIMER, and had basic training in IVP, X-ray, USG, CT, MRI interpretation. He is an expert in nuclear medicine. He has done clinical rotation in treadmill test, ECG interpretation, echocardiography, and angiographic catheter lab. He has got 10 years of experience in this domain. He has an expertise in nuclear medicine imaging, PET CT, radionuclide therapy. He has done achievements and he has published various papers and research articles in various domains of nuclear medicine with a credit of 45 research articles in the reputed international journals. He was the state second topper in school, higher secondary school, Tamil Nadu. He is the silver medalist in MD, Nuclear Medicine 2011, Chandigarh. He is the recipient of Dr. Krishnamurthy Award for Nuclear Hepatology, Society of Nuclear Medicine Conference, Chennai. He is a pride recipient of RSNA Trainee Research Award 2012, USA, considered as prestigious in the radiology wing. We are very fortunate to have you with us, sir.
Thank you, ma'am.
Yeah, he has got various travel grants. He had been a regular member and participant of academic sessions within the institute, such as seminars, journal clubs, interdepartmental scan discussions, tumor board meeting, and the list goes on. He has delivered talks in various international usefulness of PET CT, clinical validation of gated blood pool spec, European Association of Nuclear Medicine, Vienna, Austria, and he has done the role of IDG PET CT in characterization of pancreatic mass-spotting lesions and experience from the tropics, and list goes on. And he has done the diagnosis and follow-up of patients with Takshayu Artistic Society of Nuclear Medicine, India, Chennai, December 11. So we are very fortunate to have you with us, sir. Welcome you once again for this program, and we will request you for the inaugural address and followed by a talk which is very much vital for our participants.
Thank you very much for the kind introduction, madam. So it's good to see that there are 100 participants now. So we are starting with Century. So though you have given a lot of words, it's a very minimal achievement. And at the outset, I have to thank you and to Dr. Jiva who gave me this opportunity. So I just went through your university's stalwarts just to know how they evolved and how had been their background. So I just saw the achievements of Dr. Gauri, the Vice Chancellor. So he has gone to IIT, Anna University, and then ultimately to Madras University. So it's like, I think they would have definitely got very, say, extraordinary opportunities even abroad, but probably they have decided to stick to the nation and do service. And so has Dr. Madhivanan. And I think he has done a lot of work in botany, and he is the register currently. So maybe our domain in this particular week is though different, and he is a registrar in this institution. I just happen to see that different group of people have come together to give a great support to this kind of workshop. And maybe if some students are attending, I could say that this is your starting point on the career. So I'll just say that when I also started as a student, we will be in a situation, something is called as deer in the headlight. If you see or go through the headlines in newspapers, whenever deers go across the highway roads in the forest, when light headlights fall upon them, they will become static, just they will stay still. They will not know what to do. So ultimately, this will also lead to accidents of these deers. So that is the kind of situation what we students are actually in. So you'll be having lot of opportunities suddenly flashing out of us, but we will not know where to go, what to do. And these kind of workshops or kind faculties will help you guide through these kind of branching areas or stop points where you can make right decisions. So I really happy that this Madras University, which is very famous for this Georgian architecture, a very good-looking building which everyone will be willing to see. I did my graduation in Chennai in Stanley Medical College. So that was the first time for me to Chennai. Even I come from a small town called Tiruchengood. So to me, even coming to and seeing the outsides of Madras University was even a great experience for me. So I'm glad that I'm able to give some talk to the faculties and students from the same university, probably 10 or 15 years after my graduation, after coming to Chennai. So again, I wish all the students good training session, and I hope that my session also would be an interesting one. And at the end of the session, the students may think, what is the need to do so much lectures, and we come daily, do some work, go to job, and ultimately we end up doing a regular job. But what I would request the students who are seeing this meeting is, I want at least 10, I think there are 100 participants, maybe at least 50 of those would be students, at least 10% of them, that means 5, should have some patents developed in their name or in the university which they would be working. It's surprising to know that the patent office had started work when we were under the British. It was probably started in 1856. Since then, a lot of people have applied patents and many would have got. But when comparing the worldwide data, we are very much less, probably not even the top 100 or top 10 to be very perfect. And it is not a great deal to get patents. Even I feel very sorry that I have not done anything. The very purpose I got into nuclear medicine is to do some research. But with the available kind of ecosystem, I work in a corporate hospital. We cannot do a hardcore research. But when you find the opportunity, you should do a lot of research which would have a very good application in the daily practice. That is where patents convert to commercial aspects. Many will be having patents, but only few will be having money. That means that when the patent is converted to commercial aspects, so you have to think either way: getting a patent, doing a proper student job, and just think of whether that kind of research would get actually applied in the daily lifestyle. If you see the computers which we work, that means the computer in which I do the scan and report, the moment I start the scan, the first monitor, the opening screen will show the people who are involved in developing that software. So such is the kind of importance the corporate companies give to those work. So it's not that you can get or develop patent only when you are in the university and working under faculty. You can get the right job, go to a good multinational or corporate job, and then also you can develop patents, and you will be very much, ultimately money is everything. I'm not sure someone will accept this or not. You need money, and money is one way that people respect you. It's not that you are just borrowing money or you are grabbing money from someone. It is the kind of what I can say, genuine payback which you get for the kind of work you do. So I hope that the same number 5 of the people who are listening today would be getting something in the future. So I think that would be more than sufficient to deliver this inaugural address or the chief guest address. Now I move back to Dr. Chitra ma'am. Thank you, ma'am.
Thank you very much, sir, for your wonderful words. Over to Bhavani. Bhavani?
Creativity is simply connecting new dots in new ways. It's my immense pleasure in welcoming our eminent speaker of day, Dr. S. Santosh, Clinical Lead Nuclear Medicine, to share knowledge with us.
So let me share the screen, ma'am.
Yes, yes, sir. Please.
Probably the other participants should stop sharing their screen.
Jenny, stop the screen, ma'am. Yeah, it's coming, sir.
So it's a totally different kind of experience for me, because I have not given much talks to the basic science people. Maybe I would have given some lectures to those who do nuclear medicine technology. We do nuclear medicine from the doctor's side. There are also people who do the same specialty from the basic science side. They are called as a nuclear medicine technologist, and we will have interaction when we do a graduation training. But I have not spoken in front of a crowd where there are people from different domains of science, and predominantly focused on applied computer sciences in this particular workshop. Again, thanks the Dr. Chitram to giving this opportunity. So the theme of the topic is nanoinformatics on the role of nanohaptides in cancer imaging, orthodontics, orthopedics, schema, and design. So my topic will be restricted only to the cancer imaging. So this is my topic, cancer imaging and therapy using radioisotopes. So since I have mentioned the word radioisotopes, it's a kind of a material or biomaterial which we have to know in detail, which I will be telling in the subsequent slides. So the specialty which I work is called nuclear medicine, and it has different technologies called SPECT imaging, PET imaging, or molecular imaging. So before going into the topic proper, so let me just take some journal on what is their outlook or what do they feel about nanotechnology in cancer diagnosis. So this is one of the papers which have been published in 2019. So what do they say in this? It's a known to everyone. So if we have to diagnose cancer, the earlier we diagnose, the better the treatment. Hence, the quality of life of the patient will be better. Usually people will be thinking that once someone develops cancer, it is like the end of the world. It's not like that. Actually, there are situations, even kids, 2-year-old kids, 10-year-old children, they may also develop cancer. But if we diagnose at the right time and treat the patients at the right time, we can deliver a very good exceptional quality of life to those patients, and at least 10% of those patients can be given complete cure. And this mainly depends upon the time point at which we do the management. So cancer can be diagnosed either by 2 ways. Either when the patient comes with a problem, the patient says that I have some stomach pain or I have difficulty in watching, then the doctor will do some test, and one of the tests will be taking a blood sample, and the other test is doing a scan. So these are the 2 ways by which we diagnose any problem, not only cancer. Either we go by blood test or by doing a scan. So scans, you know that there are many scans like CT scan, MRI scan. Some advanced scans are called PET-CT scan. That is the modality in which I work. So in nanotechnology means obviously whichever substances which you use should be having a size within the margin of nanometer, that is 10 power minus 9 meter. So the size of the molecule should be very small, and this molecule should be administered into the body, or else some body substances should be taken out from the body, and those substances will be mixed with the reagents. The reagents are designed as nanoparticles. So ultimately we get some results. So based on the results, we do interpretation. So basically, what are the barriers when we go by this kind of approach? Suppose a patient has, everyone know that people develop lung cancer, and they develop cancer in the bowels. That means the stomach and the tubes which connect the stomach. So when these kind of organs develop cancer, those cancer cells, they secrete some substances in our body. So we can take some blood sample and measure whether these substances are present in higher amount or not detectable. Suppose if they are not detectable, we can say that they don't have this kind of problem. Suppose if they are detectable, then we can have a clue that this so-and-so patient has such kind of problem. But to address this, when we approach this kind of method, there are some barriers. What are those? Low biomarker concentration in the body fluids. As I gave the example, lung cancer. Say the cancer has secreted some 10 molecules of a substance. So when you take a blood sample, it is say a random chance, or it is a very low probability that one of those molecules will come into the blood sample which you have taken. So if the concentration is very low in the body fluid, you may not diagnose that. And say the lung cancer secretes a substance A, there will be some other substance in our body B. These two substances will be having very close similarities. So if they are very similar, that means the cancer molecule is also looking very similar to the normal molecule, then it will be very difficult for us to differentiate these molecules. And the third difficulty is whichever molecule which we put into use for daily day-to-day practice, that is called clinical use, we have to do a lot of research in with so and so substances. Suppose I am saying that a molecule A can definitely 100% diagnose cancer. Then what I have to do is I have to take, say, 1,000 patients or 10,000 patients, take the blood sample from all these patients and take the sample and measure this molecule. And then say 100 patients has this molecule A in their blood sample, then I have to prove that all those 100 patients had cancer. So this is called prospective study. We are taking a group of people, taking a sample and following them over a period of time. So this is how prospective studies are conducted. This is kind of a research study. So it's very difficult to carry out these kind of studies with the large population groups. So these kind of barriers are there when we apply this kind of technology. So how are we going ahead breaking these barriers? So this is the same graphical representation of what I told. So to do or measure any kind of problem, we have to take some representative molecule from the body, or we inject some molecule which goes inside our body and binds to the organ or region of interest. So there are different kinds of molecules in our body. They are called as proteins. The DNA from our cells, if they get broken, they can come out of the cell, they can circulate in the body. Even the tumor can detach from, one tumor cell can detach from the organ and it can circulate in the body. Like this, there are many molecules which can be used for this detection. So they have classified this into three major spokes. One you can have here as a detection of biomarker, that is taking the blood out of the body and doing some test. Detection of cancer cells. Here we take the molecule, we take blood from the body and we just see whether the cancer cell is directly present. How can we see? We can see the molecules which are secreted by the cancer. And the third modality is by in vivo tumor imaging. You should just understand by the word what is vivo. Vivo means body. In vivo means within the body. So that means we are doing the test in a alive patient. When a patient comes, we subject the patient to some kind of scan, and by doing the scan, we diagnose the problem. So nanotechnology basically uses three different types of particles. They are called as quantum dots, gold nanoparticles, polymer dots. These are still in the research phase. Information I'm going to share in the subsequent slides, they are not at all related to this, because what we do here is what this nanotechnology is currently is research phase. So these are the examples of particles. Basically, these particles have a size of less than 10 power -9 meters, and these particles have some specific properties so that they can be easily studied with different technologies. We just cannot do imaging with a nanoparticle. Suppose if you take a particle from the blood and take that reagent and bind the reagent, it should glow, it should emit light, it should cause some change. So that means there should be some enzymatic reaction. They should have some kind of potential that they can emit light. So then only we can capture that information and say that something is present. So these particles have that kind of properties. So that is why these kind of particles have been developed and they are still in the research phase. So I will skip. So this is nanotechnology for in vivo imaging. The previous slide says these particles are used mainly in the research phase, whereas this current slide says whichever particles which we use in the clinical phase, that is the real-time practice. So this is one of the table which had been given in the journal journal article which I referred to. So in which they say that different kind of cancers have been studied with this kind of nanotechnology based particles. And at the end of the table, they say that PET imaging is commonly used these days. So in my subsequent slide, I will say what is this PET imaging. So now coming to the main course of the lecture, which is our specialty, which is nuclear medicine. So the specialty developed with the invention or the discovery of radioactivity. So what is radioactivity? Radioactivity is given by the statement, emission of energy by unstable nucleus, either as particles or electromagnetic radiation. Just simply, we know that our body, we are made up of carbon, nitrogen, oxygen. So these kind of particles are come together, make DNA, and that is how our body is made. So our body doesn't have this kind of radioactivity most of the time. The radioactivity will happen only when a nucleus becomes unstable. So at what point does a nucleus become unstable? I will tell the subsequent slides. So that is the point when a nucleus becomes unstable, and if it becomes unstable, it will emit energy. That energy will be captured as radiation. So to make it simpler, suppose we are patiently listening to this topic. Suddenly I am very boring. You get very angry. So the way you express anger is whether you switch off the presentation, you go off. So that is one form of expressing your anger. So this radioactivity is one form of expression, or the form of expression by an unstable nucleus when it becomes unstable. So this is the inventor, or the named Henry Becquerel, who discovered the radioactivity. He discovered in the year 1896. It was an accidental phenomenon. What happened was he was working with some particles in his lab, and he left for a job. And the next day when he came, he could see that some kind of images were there. And this what happened, how it actually happened was he demonstrated that by keeping his kind of emblem which he was having, that shade of the emblem was not seen, whereas whatever spaces outside this emblem was captured. That means some radiation has passed through this metal, and this radiation was blocked by the metal. You can see that the area behind the metal is not showing this kind of activity, whereas the areas outside the metal show this kind of blackish areas. That means there is something happening, and something is passed through this metal that's absorbed by the metal, whereas whichever areas there is no radiation, whichever areas there is no metal, those areas the radiation has passed and caused some change in this paper. So this is the first phenomenon how radioactivity was discovered. So this is a simple phenomenon. The radioactive atom emits energy. That energy can be either in the form of radiation. We see TV, we read books. These are all possible only because of visible light. Sunlight is a form of visible light. When light falls on a substance and the substance reflects, then you see the light. Suppose if the light falls on a blue colored object, it means that out of the 7 different colors of radiation, there is VIBGR, the blue color object will absorb all other colors except blue. It will give back blue color. So that is how we see a blue colored object as blue in color. When all the colors merge together, it will see only as a white light. So this is a visible form of radiation. Whatever radiations which I say in this, they are invisible form of radiations. So that is one another specialty to this kind of radiation. So that is why whenever an atomic bomb explosion happens, that is also radiation only, but you cannot see the radiation. You can feel only the heat that happens from the radiation. The other form that's radiation can be made is a particle. They can be really small particles. Some you can imagine like a billiard ball, but it will be very, very small in size that you cannot even feel that that particle has hit your hand. It will be very small in size. So this is the phenomenon of radioactivity. So this is a specialty which I work in, the nuclear medicine, which uses radiopharmaceuticals to investigate disorders of anatomy, physiology, and pathophysiology. And based on this, we either treat or diagnose problems. Okay. Now we have to know something about everyone know that we do a lot of X-rays. And X-rays is used for diagnosing a lot of fractures, some bone-related problems. So you will always know that whenever you go for X-ray, the radiographer who is doing the investigation will ask you to lie over a table. They will switch on a machine. Some rays will pass through your body. You will not feel that something has passed. So that is the example given here. The X-ray from the machine passes through the body and hits on this detector. This detector will measure how much X-rays has passed from your body, and based on that, it will give an image based on which we find out the problem. But the gamma rays, which is the rays used in nuclear medicine, these are totally different from the X-rays. How? The gamma rays cannot be emitted or produced by a machine. The gamma rays are emitted by unstable nucleus. This is what I said in the previous slide. So we have gone through a periodic table in the chemistry where a lot of elements will be there in the rows and periods, which you will somehow remember. And whatever atoms which you see, hydrogen, helium, phosphorus, whatever, they will be in their stable configuration. That means they will have some amount of protons, neutrons, and only that configuration will be displayed in the periodic table. Whereas whatever unstable nucleus which could emit radiation, they will not be displayed in the periodic table, but they are just brothers of the same elements which they use. I'll just show in the subsequent slides. Maybe some concepts of this will be somewhat difficult for you to understand, but when I go through subsequent topics, it will be easier for you to understand. So this is how you can imagine how an unstable nucleus will look like. And you can see the X-rays are emitted from outside the surface of the nucleus, whereas the gamma rays emitted from the inside the nucleus. So this is atomic nucleus. You can imagine any atom, hydrogen, helium, whatever atom, whenever it is unstable, it will emit radiation like this. So now you have to know something about the physics of radioactivity, radiation detectors, emission computed tomography, PET, and how these modalities are applied in clinical practice. So this is a diagrammatic representation of the hydrogen atom. So this atom will be having a proton in its nucleus. I think you definitely remember something like this study in your 8th, 9th physics. Something called proton is there in the nucleus and neutron. So hydrogen is the basic or smallest atom which has one proton into its nucleus. That's only that much is the size of hydrogen. But suppose if a hydrogen atom has another neutron added into that nucleus, then it is called by the name deuterium. If it has two more neutrons in addition to the baseline configuration, then it is called as tritium or tritium. So this hydrogen will be stable. It will not emit radiation. And this is the hydrogen which is present in our body. And this is the hydrogen which makes the water molecules which we drink. But there are radioactive hydrogen atoms when the hydrogen nucleus has one or two neutrons in excess. These kind of atoms are called as unstable atoms with unstable nucleus, and they are called radioactive atoms. Only these atoms emit radiation. The radiation will be either in the form of simple gamma rays or particles. So basically these are called as isotopes because they have the same atomic number, that is 1. Atomic number means they have the same number of protons. So one proton, one proton, one proton, but different number of neutrons. When any atom has this kind of configuration, they are called as isotopes. When they emit radiation, they are called as radioisotopes. Only this much is a simple concept. So like we measure electric current by the unit ampere voltage, this radiation should also be measured, right? So the unit of measuring radioactivity is called Curie. You would have many, I think most of you are aware of this Nobel winning lady scientist, Madame Curie. And to honor her, since she had played a great part in the invention discoveries of radioactivity, her name had been given to the unit of activity. So only this much is needed to be remembered. So basically what means radiation is, say there are 100 atoms here and only 50 atoms are radioactive. Those 50 atoms will emit radiation. So then we will say that there are 50 radiations happening per second. So basically radiation is a phenomenon which actually happens per unit of time. That's what we need to remember in addition. So basically when the protons and neutrons are not in the proper proportion, they become unstable and they emit radiation. So again, I am repeating the same concept. The radiation can be either in the form of rays or it can be in the form of the particles. So you have to remember just two basic particles. One is alpha particle and the other is a beta particle. So how these radioisotopes, I have spoken a lot about radiation, and I'm saying that our body is not made up of any radiation emitting particles. That means in nature, most of the atoms will be stable and they will not emit radiation, except for very high atomic number molecules like uranium. If you have gone through news, if you read about Russia or you about nuclear warfare, you would have come across a term called uranium. Uranium is an atom with a very high atomic number. Only those kind of atoms will be unstable even when they are just in the nature. They will emit radiation. But most or 90% of the atoms in the nature will not emit radiation. But we can make them radioactive by artificial methods. So those methods are done by machines or equipment. So one of them is called nuclear reactor. Again, you would have heard a lot about nuclear reactors. And another machine is called cyclotrons. The cyclotron also is a topic which you have read up in the school physics. Using this kind of equipment, we produce this as radioisotopes. So basically, how do we do the scans? So a patient comes, say, if a patient has a problem, and the doctor says that I want to know something happening in the patient's body, and the patient will refer to our department. So what we'll do is we'll just look back the history, what has happened to the patient, and we'll select the right kind of molecule, because we can study different parts of the body, right? So some patients will be having cancer in the lungs, some will be having cancer in the bowel. So we have to select the right molecule. So that molecule will be selected first, and this molecule will be tagged with the molecule which is capable of emitting radiation. So there are two molecules. One is a molecule which is capable of emitting radiation, another is a molecule of interest. So these two molecules have to be added together. So that is demonstrated in this picture. So after this, that is taken out of that vial and injected in the patient's body. Obviously, it will go and get deposited in the cells in the patient's body. And then the patient will be made to lie in the scanner. The scanner will be looking something like this. I will show in the subsequent slides. And ultimately, you will get a scan like this. For all these applications, we need a lot of support from the basic science. So without computers, none of this is possible. And I will again reiterate the role and importance of computer applications in the subsequent slides. So this is a kind of equipment called generator, in which we get this molecule, and this molecule is added to the organ molecule of interest, and then it is injected into the patient's body, and then the scan is done. So this slide is just to say that there are different kinds of molecules that we can decide, and based upon the region of interest, we'll inject that particular molecule. Suppose a patient is having cancer, and referring doctor wants to see if the cancer has spread to the bones. Bone is the most common site where cancer can spread when the patient is in stage 4. Suppose we have to study the entire bone, we will select this molecule called methylene diphosphonate. This molecule will be tagged with a molecule called technetium, which can emit radiation, and then it will be put into the patient's body, and then we will do the scan. So this is how a scanner will look like. And the name of the scanner is called gamma camera. I will repeat again, gamma camera, because gamma rays are captured by this camera, and that's why it's called gamma camera. It is a simple name. Technically, it is called as SPECT scan. That stands for single photon emission computed tomography. Single photon, that means a single ray is emitted from the patient's body. That is single photon emission. Then CT stands for computed tomography, because all this information is computed by the computer system, and it gives the images. That's why it called as single photon emission computed tomography. So when the patient lies like this, we have already injected the radioisotope inside the patient. You can see some, we technically call this as an IV camera. You can just understand that this is the port through which we give the injection, that it is fixed in the patient's hand, and then the patient is made to lie in the scanner. This radiations will come out of the patient's body and hit the detector in this camera, and the images will be processed. And in real time, we can see that some white cloud images here. These are the actual images that are being captured by the camera, but you cannot see the rays here. That is why I said these are invisible radiations. But the computer can detect, and the other detectors can detect these radiations. They process and give the images. So what kind of processing is done? I will show you. So like any television or any computer, all these have a set of inner construction. One is called a detector or crystal. This is the material which detects the gamma ray. When the gamma ray hits the detector, it will sense that something has hit this and it will give an electric signal. I will tell you in the subsequent slide what happens. After this, it goes through a series of circuits called preamplifiers, amplifiers, analog to digital converter. Again, without computer, this is not possible. Ultimately, it is the process by specialized software, and then we get the film with which we do the reporting. So I told you that the gamma ray hits this detector, and then the system senses that something has happened. So what actually happens is called, the phenomenon is called scintillation, given by this spelling, scintillation. Whenever certain materials absorb radiation, I told these radiations are not visible, and when these radiations are absorbed by that materials will emit electrons. So obviously, you know, the electrons are not, electricity is nothing but transfer of electrons. So we cannot directly measure the radiation, but we can measure the electrons which are emitted by the radiation. So those electrons are calculated by the system and give us images. So what happens is whenever the radiation hits, you just imagine that this is the detector over which the gamma ray hit, and the gamma ray hits, the electron in that material will gain some energy and again comes back to the baseline state. At the time it emits the photon. It will be a little complex for you to understand, but this is a simple mechanism which happens in the detector. I thought that it will be incomplete if I don't tell this concept. You just need to know that something called scintillation happens in the detector, and that gives current. Ultimately, current pulses produced rays hit the detector, and this is transferred through something called photomultiplier tube. You can see here this is transparent. This will carry the light waves, and the other one you can see electronic circuits. This will carry the electric current. So this will be ultimately processed by the computer. So these are the processing which happens. So like any, as I said previously, we ultimately see all the images in a television or a monitor, which is LCD monitor. These days we have LED monitor. Obviously, they'll be having the same concept called pixel matrix size. And when we see the scan as a simple scan, 1-point scan, we call that a static scan. When we see a dynamic image, a cine loop, we call that as dynamic scan. And it has a lot of processing with filters, which I will be going through, taking you through subsequent slides. So ultimately, we get a scan something like this. I think now you will feel relieved with my boring previous speeches that something is colorful shown now. So this is called as bone scan. So this is the scan of a patient who has no problem. This is a normal looking scan. You can see that, you can understand that these are the spinal columns. These are the bones in the legs, hand, and the skull. So this is a normal expected distribution. How this scan is done. We have injected the molecule called MDP. The MDP has gone into our body. It has deposited throughout the bone. It has gone and bound to the surface of the bone. And this MDP is tagged with another isotope, radio-isotope, which can emit radiation. So from all these areas, radiation will be emitted by the molecule which is seated there over the bone. So the detector will get hit by the radiation. It will sense signals, and the signals processed by the computer, and ultimately we get a scan like this. So what the image would look like if a patient has cancer? It will be something like this. So now you see the difference. Here it is looking homogeneous, symmetrical. But whereas if you see here, it is not homogeneous, it is randomly seen, and you can see multiple areas of very high contrast or high brightly lightened areas. So these are the areas where there is more amount of cancer. So those areas, there is lot of cancer cells, and because of that, there is lot of bone material present in those areas, and the injected substance is going at a higher rate to those areas which is having cancer compared to the sites which don't have cancer. So this is how we make the difference. When we do a scan for a patient with suspicion of bone metastasis is the cancer has spread from the original site. So here there is no evidence of bone metastasis, whereas here you can see there are multiple sites of bone metastasis. So this is a simple example of how image looks like after going through all the physics, computer every processing. So previously I told that this detects images, and if you see, this is something like two-dimensional picture. You are just seeing the patient from standing behind a friend, something like this. But if you want to know the depth of information, what is happening inside the patient's body and at what distance this lesion is from the center of the body, we need to know that 3D information, three-dimensional information. So for that, what the inventors have done is they have devised such a system that this is called the detector. The detector will go 360-degree around the patient so that it will give us a three-dimensional information. So this is also possible again with the applications of computer. So if we see this cartoon lady from this side, you will have image something like in the lateral projection. But when we see in the back, from the backward projection, you will see only an image like this. You will not know what is happening. Actually, if you see this lady is holding some jar or something, but it is seen only in the lateral projection, but this jar is not seen in the backward projection. So unless we have a three-dimensional information, most of the information will be lost. So this is where that technology is called SPECT, single photon emission computed tomography. All the information which is collected when the detector goes around the patient is taken by the system, and it processes and gives us an image. So these are all done by the algorithms this written in computer. So what would happen? Again, going back to the previous example, you can see that there are two images, one here and one here. Suppose, and this is two images taken at 90-degree angle. Suppose if you have taken the image at every 3-degree angle, you will have more information, and all the information will be crisscrossed, and ultimately you will get the true information. Something like this. So this is a representative example of the, we can say, imagine that there is a thyroid gland. Thyroid is a butterfly-shaped gland which is seen here, and this is a representative example. And when, suppose, if you just have taken the scan only from one view, you will just see only from that side and will not know what is happening on the other side. But since here, 32, you can see that this, after taking 4 views, the image looks something like this. After taking 8 views, the image looks something like this. And after taking 32 views, you get the image something like this. So the more number of views you take, the true or the nearer the information will be. And it goes through a sequence of processing filters, which I will be telling later. So this is an example of how this is the image of the heart. It's very difficult for you to understand this is a heart. Maybe you will think that this is like a fish slice, but this is the slice of the heart which is taken at different levels. Only we have taken a 3-dimensional information. We can say in some areas of the heart that you can see that here the thickness appears uniform, whereas here you can appreciate that the thickness is fixed. That means the infarction, that means heart attack has happened in these regions. Suppose if we have taken a view from this side only, we will not be able to appreciate these kind of changes. So only when we are able to do a 3-dimensional imaging, we can get this kind of images. So till now, I have told that whatever scans which we do in the nuclear medicine are called SPECT, single photon emission computed tomography. You all know that there's something called CT scan. CT scan is done in the department of radiology. In CT scan, if you go back to the original image which I showed, X-rays are passed from a machine. The machine X-rays pass through the body and comes out of the body. So there is no specific design of any molecule. We just pass the rays across the body. The rays come out and you will tell how many areas absorb the X-rays, how many areas didn't absorb the X-rays. Suppose if the X-ray passes through the lungs have predominantly air. So this is the area where the air passes and goes out. It gives us oxygen. So when X-rays pass through this area, predominantly this area is having lungs. The lungs will not stop the X-rays and you will get a black image. Suppose if the X-rays pass through your bones will absorb all the X-rays and you will see a white type image. Now you can recollect, if you see any X-rays, all the bones will be appearing white. So in a CT scan, you will just see black and white images and it will tell us whether bone is present, whether there is any destruction of the bone, whether muscle is present, whether any deviation of muscle. So this is how a CT scan will be. So that's called anatomical imaging. That means we just see the anatomy indirectly by passing a X-ray. What we do in SPECT is we are actually studying the function, because we tag a molecule of interest. That molecule goes inside our body and gets deposited in the organ of interest, and that particular organ is visualized. In cancer, we target the cancer producing molecule and it goes and binds only to that particular cancer. So what would happen is in CT scan, we just see only the anatomy, whereas in SPECT scan, we see the function, pathophysiology, everything. So when these two are combined, it is called as hybrid imaging. That is why SPECT is shown on this side, CT is shown on the other side. And when these two combine, we do something called SPECT CT. So this is the ultimate advanced current technology which we use on a daily practice. So this is how, as I told you, the CT scanner can be inbuilt along with the gamma camera. These two heads form the gamma camera, whereas this is the. So again, this was also possible only because of the images from the CT have tagged or along with the. I think someone has to move.
Please kindly mute your audio.
Okay, thank you. So I think that was one way giving a break for some if he had the boring session previously. So now coming to our session here. So this is a CT scanner and this is the gamma camera. So here two technologies could be fused only because of computer applications. When we take images from two different scanners, both the images have to be exactly superimposed. That means the image from functional information and the image from CT scan should be fused together and we have to get the information. So this is a hardware in which the scan will be done. And this is how an image will be looking like. This is the image which we obtained from a gamma camera. This is called planar imaging. And then I told that we'll be doing three-dimensional images around the patient's body, what we call a SPECT imaging. The image will be looking something like this. And this is done by the gamma camera. When we fuse these images with the CT scan, then it is called as hybrid imaging. It means CT as well as gamma images are fused and ultimately we get an image like this. So this is a doing a combined imaging. Why should we have a combined imaging? Suppose here I say that there is an abnormality here. Many structures will be present here. Heart will be present here. Blood vessels will be present here. Bone will be present here. But when I see from here, I will not know whether this is seen in which organ. When I do a three-dimensional imaging, now I can say that this is not in the bone because if it had been in the bone, it will be seen either here or here. Now I can get some information that within the center of the body, but still I don't know which part in the center, which organ has this. So when we do a CT scan and fuse these two scans, then now I can say that this is sitting on a lymph node or some structure called parathyroid, and that is the lesion which we wanted to see. Suppose just if you think only CT scan had been done, a CT scan will be giving an image something like this, and you will not know what is happening here. But only when both scans have been combined, now we can see that there is an abnormality here, and this abnormality is localized to a structure here. And by giving this information, the surgeon now will be able to dissect the body and take this structure from here. So this is the advantage of doing a hybrid imaging. So these are the different hybrid scanners. As you see, the first commercially available scanner came in the year 1999. So now we can understand that these are all very recent developments. But if you recollect, I told that the concept of radioactivity was discovered in 1896. But the commercially available, this kind of scanner is available only in 1999. That means we have to wait for almost 103 years. Again, it is only due to the rapid processing and the computing skills of computer only this had all been possible. So the actual raw material was available. But to make the raw material being utilized, we have to wait for complex calculations. We cannot do complex calculations manually on a faster basis. So we need computer algorithms. So only when computer algorithms developed rapidly, we could get this kind of scanners. So these are the prototypes and how those scanners look like. So this is the kind of scanner which I showed in the first scan. So the next technology is called PET scanner, positron emission tomography. Previously, I was telling about something called a single photon emission computed tomography. The second machine is called positron emission tomography. Again, if you recollect, I told you that any unstable nucleus will emit radiation. it could be either in the form of gamma rays or it could be in the form of particles. In the particles, I told there are two different types. One is alpha particles, and there is beta particles. Those beta particles are used for doing imaging, and the beta particle is conventionally called positron emission. So we know that electricity has positive and negative charges. The same way, these particles also have positive and negative charges. A positively charged beta particle is called positron. It's for you to remember. Positron is nothing but a positively charged beta particle. So how we do scans with this? So this is the scanner. So this is a scanner available in a hospital. So you can imagine that this machine is somewhat different to the previous machine I showed. And this is having a ring kind of configuration. In the previous machine, there were two different heads and they are rotating around the patient. Here, since there is a ring of detectors around the patient, there is no need for any motion in this case. These are stationary detectors and they will detect the radiation 360-degree angle. Here also, the radiation is being emitted from the patient, but here positron is emitted, whereas the previous example, gamma ray was emitted. So that is a difference. So this is a technology which is currently being employed widely for studying most of the cancer applications. So if SPECT is a conventional technology, PET-CT is the advanced technology which we use currently. And as you can see by the name here, this machine is produced by Siemens, which is one of the world leaders in making household or any medical or any other electric equipments. And the name of this model is called Biograph Horizon. So I previously told that positively charged beta particles are called positron. So when this positron interact with a negatively charged beta particle, it's called negative. This mentioned by the same minus here. What would happen is these two particles will get neutralized. So you can just simply think you have seen if there are any 90s kids in this forum, you have seen some teleserials where in Ramayana and Mahabharata, when they launch arrows, these arrows from the hero side and the villain side will get dashed and they will just disappear. So the same thing happens here. So these things had probably somewhat known to our ancestors in some way. So when these two particles of opposite charge get collided, they get disintegrate, they disappear. But energy can never be destroyed. So the energy in the form of particle is emitted in the form of rays. These particles are now converted to gamma rays. But only difference is here, two rays are emitted in opposite directions. So suppose, imagine a patient lying here. There is a tumor or there is a cancer in the part of the body in the patient here. Here the positron will have gone and bound to the cancer cells here. And from here, they will emit radiation opposite directions, exactly 180-degree apart. So there is one radiation going across and another radiation across. So in this way, both the detectors across 180-degree will simultaneously detect each event. This is called coincidence detection. So these things happen in nanoseconds or less than that. So to measure these directions in the same time frame, again we need computer to process this information, because each second there will be a lot of radiations and each coincident radiations will have to be detected by the system and they have to be true. So this is a schematic representation. A patient is lying here, the radiations are emitted. I told you there is a ring of detectors and this is collected. There's photon hits the detector, and as I told previously, they are converted into electric current. This is processed by the system. I told there is something called coincidence. These two rays are detected simultaneously by the system and they are processed by the system. Just like this. This is again the same principle which I told previously. So previously I told gamma emission. Gamma emission, I gave an example. There is some radioisotope called technetium 99M. Whereas in positron, there are a lot of unstable atoms with unstable nucleus. If you remember, carbon will be in the left-hand side of the periodic table, and the carbon is one of the very basic molecules. Actually, the mass number, that means the total number of protons and neutrons in a normal carbon molecule will be 12. Whenever any atom has one or two neutrons lesser than the baseline, then that atom will become unstable and will emit positrons. So I have given many examples like this: carbon, nitrogen, oxygen. None of these are present in nature. All these are produced artificially in the equipment called cyclotron. But the most commonly used unstable nucleus is that of fluorine 18. And I want you to remember this. This will be helpful in your subsequent exercises. So this fluorine 18 is the most common positron emitter which we use currently. So I told this is a molecule which is used to do a cancer. So what scientists invented or they got to know was whenever there is a cancer, it has to grow fast. So any cancer cell will be growing fast. So when we have to do a lot of work, what we need, ultimately we need more energy. So if we have to give more energy, how will the cells get energy from our body? If you see an ad, you will see that some kid is drinking Glucon-D and it's faster and running faster. The same way, this cancer also takes a glucose molecule in our body. It means actually it extracts a glucose molecule which is available in our body and it grows faster. So this was discovered by scientists who work in cancer. So that the same principle was captivated in this technology. So what scientists did is, I told previously that there is a positron emitter called fluorine 18. They tag the fluorine 18 with glucose. So they take the glucose molecule and they take the tag means just adding fluorine 18 with the glucose molecule. Ultimately, this is called fluorinated deoxyglucose. So this is again the same glucose molecule, but the only difference is this will emit positrons which will be captured by the system. So when we inject this molecule in a patient having cancer, it will go into the patient's body and it will emit radiation. The system will pick the radiation and will generate images. So we'll see. So just to say that this glucose molecule has the size of 10 angstroms. So obviously this also fits into this nanotechnology concept. This is how an image looks like when a 7-year-old girl or a 17-year-old boy had been injected with this radioisotope and the scan is being done. So whatever you see in this scan is not abnormal. These are normal. You can see that the brain is seen. You can visualize that this is the top of the head. So obviously this is the brain. And here you can see, I guess you'll accept that there are pair kidneys. You'll have seen, if most of the audience from Tamil, you will know that there are 2 kidneys told by Vivek in a famous comedy. And this is excreted into the bladder. So what we see is the injected glucose molecule is taken by the brain. Obviously, brain continuously works, so it makes more energy. And if you see here, you can see the heart here. Heart also continuously pumps, so it needs more energy. So these are the normal distribution of this molecule, which is called as biodistribution or physiological distribution. Physiologic means what is normally functioning in nature in living systems. So this is a normal distribution. What if some person has cancer, and let's see how that image looks like. So this is a rotating image. I've just shown you just to generate more interest. We can make it rotating at 2-dimensional. So only because there's a ring of detectors, we took 3-dimensional images and we can make it rotate around. So you can see that this is the urinary bladder. This is normal because the glucose molecule was excreted into the urinary bladder. But whatever you see above in the upper half, these are all cancer cells. So this patient had cancer and cancer cell has distributed in these parts of the body. And this cancer cell had taken the glucose molecule and it was emitting radiation and is collected by the system and it gave us the image like this. So it is easy for the treating doctor to find out at what stage the cancer is and which part of the organs it has spread to. So based on this, we can select the correct kind of treatment, either to do surgery to remove the cells or to give some injections. So I told previously that whenever the patient has cancer, the cancer cells need more energy. That is called hypermetabolism. So this is the concept based on which this imaging is being done. So we can interpret the PET scan. I told you that there are some lot of black areas and this is cancer. I cannot give this kind of report to your doctor. I have to give technical information. So when you do a thesis, you do a lot of analysis, right? There are a lot of parameters. Similarly, there are a lot of parameters while interpreting these PET scans. So what are the kind of parameters? These are semi-quantitative parameters. They are called a standardized uptake value. It means compared to a normal cell, suppose a normal cell takes 1 glucose, how much molecule this cancer cell has taken. Suppose the SUV value comes as 10, that means it has taken 10 times more molecule compared to a normal cell. This is for our general understanding. So when the SUV value is higher, it means that the cancer is more voracious. It takes more energy. When the SUV value is less, say 2, 3, then it means less voracious. It is a subtle form of cancer. So this is one way of understanding how a cancer looks like. So I told that mainly this is used in cancer. There are other non-oncological applications. That means not only in cancer, we can use this technology in reading many normal, suppose a patient has tuberculosis, a patient has heart attack, a patient's epilepsy. In those situations also we can do this scan. But in this topic, since the theme is limited to cancer, I'll just show few images of how this technology is used. I just want you to know some terminologies called staging, restaging, treatment response, surveillance. Diagnosis, I have already told that whenever a patient freshly comes, you are detecting that there is a problem. That is called diagnosis. Suppose a patient has come with a cancer in the lung. So you want to know, basically many of you would have heard about what is the stage of cancer, 1, 2, 3, 4, something like that. Suppose the cancer has spread to multiple areas, that is called stage 4. So for staging, you need to know whether the cancer has spread to different parts of the body. So in that way, this scan helps. And another is called treatment response. Suppose a patient has cancer, you have given some treatment, and the patient comes back after 10 years, 10 months, or 10 days. Then you need to know how much cancer has reduced, or whether the patient has been completely relieved of disease. At that point of time also, you can do the same scan and see what is the difference or how much reduction has happened. That is called treatment response. I'll give some examples for this. So it will be very complex to show these things. I just imagine a patient who has a complaint of back pain, and they have done some MRI scan, and the MRI scan shows cancer in the some doubtful cancer in the bone. So whenever there is cancer in the bone, I told that they would have probably spread from other areas. So for this patient, they have referred to the FDG PET scan to see if from which part of the body the cancer has come from. So we did the scan. So the scan showed lesion only in the same areas. This is the vertebra, this is spine in the back of the body. Only 2 lesions were seen in the spine. That means in this patient, the cancer is limited only to the spine. It is not present anywhere else. That means primarily the cancer has developed in the vertebra. So that is primary cancer from the bone. So it's technically called as multiple myeloma. So in this case, PET scan has helped in arriving at the diagnosis, which was initially having a doubt whether this is metastasis. I have previously told metastasis means cancer has spread from some part of the body to other part. So here this is not metastasis. Cancer has actually originated in the bone, and this disease is called multiple myeloma. You can see that if you see only the CT scan, you cannot see there is a significant abnormality seen here, but here you cannot appreciate the abnormality. So that is the advantage of doing a hybrid scan, that the CT scan and the PET scan are fused together. I will give another example. So this patient had a disease called lymphoma. Lymphoma is a cancer which is involving the lymph nodes. Since many of the audience will be speaking Tamil, Tamil neri kadirukku solluvom. So அந்த இடத்துலயே cancer வந்ததுன்னா அதுக்கு பேர் lymphoma. So lymphoma also can spread to different parts of the body. So in this patient, this is a whole body scan. We can see the dark colored areas are seen here, and also in abdomen also. So ultimately what we found out was cancer was also involved in the bowels. So initially, if only CT scan had been done, they would have thought that the cancer was seen only in the neck. But by doing the scan, we came to know that the cancer spread to the left side of the axilla. We can see in this image, and also within the abdomen. So by doing this, we came to know that this patient has stage 3 disease and not a lower stage. That means this patient has a higher stage disease. So till now, I was speaking about the tracer fluorodeoxyglucose, which goes by the principle of hypermetabolism in cancers. But in my first few slides, I have told that different molecules in the cancer cell can be targeted to make it specific. So I'm just coming to that topic now. So DOPA is one of the molecule. This is called dihydroxyphenylalanine. Basically, this molecule is expressed by only certain type of cancers. And when we inject this molecule, only those cancers will be shown in the scan. And there is another molecule called DOTA peptide. So this is expressed by another set of cancers called neuroendocrine tumors. So only those tumors will express this kind of molecule. And when we inject this molecule, this will bind to those cells and tell us that this kind of cancer is present in the body. I will give you the examples. So I was telling you about DOPA. This molecule was injected. And if you see, this is the body and this is a liver organ. Here there is another organ called pancreas. This is the tail end of the pancreas. These are all background physiological distribution, which I told previously that the normal expected distribution of any biomolecule is called physiological distribution. So that is background. But here you see there is something higher than the background. So there is a tumor in the tail of pancreas, and this is technically called by the name insulinoma. So by giving this agent, we were able to diagnose insulinoma. This is very specific for this particular type of cancer. And coming to another example, DOTA. So I told you this is used in neuroendocrine tumors. So this is the normal expected distribution of this agent if injected into the patient's body. So what would happen if some patient has cancer from this kind of cancer? So you can see there is this is a lung. This is a corresponding cut taken at this level. And if you see this image, we can see that there is a structure here. But if you do only the CT scan, it will be very difficult to appreciate. But by giving the contrast in the form of this radioisotope, you can diagnose that this patient has a cancer containing this kind of molecule. So coming to the last example, I told you this technology can not only be used to diagnose cancer, it can also be used to see how the treatment is getting succeeded. Now you can see that there are a lot of cancerous areas in the liver here, but after 9 months of treatment, you can see the lesions have drastically come down, and after 4 years, they have completely disappeared. So this is the proof of that treatment being completely given. So by showing this image, we can give a reassurance to the patient that currently the patient is symptom free. If they simply say that you are cured, then it will be difficult for them to understand, right? But if you use this kind of image, it will be easier for them to understand that the cancer is completely cured. So it is technology is not only used for diagnosis, it is used for staging to see the different spread of disease, and is used to see whether the disease which was once diagnosed has now responded to treatment. So coming to the last application, that is treating the patients. Till now, I have told that only the scan is used to see or map the extent of disease. But by giving the different kind of molecule inside the patient's blood vessel, we can even treat the cancers using this technology. So I told you that we use something called beta particle. I'll just show you something as simple cartoon. So these yellow color light end particles are the beta particles. They go by the blood vessel, they go into the cancer cell. Ultimately, they go from the wall of the cancer, they go into the cancer nucleus. Even cells also have nucleus. And this radiation will go and destroy the nucleus. Once the nucleus of the cancer cell gets destroyed, obviously the patient will be cured of the disease. So this is one example. So here there is a patient having a cancer here. This patient was treated with that kind of technology. And you can see the size has come down now. And after a few more cycles of treatment, you can see again it has drastically come down. So in nuclear medicine, we will be able to treat as well, also see the extent of the disease. So we cannot just like that inject this medicine into the patient's body. It needs a lot of research. So this is how the research happens. So the research usually happens in the animals, lab animals, and then they will be doing a lot of reagent studies, and all this information should be properly tabled up. There will be a lot of Excel analysis. Again, for Excel analysis, you need complete applications. And then they will be coming to market. We need the industry support. That is corporates who run the business, and they will be funding this trials. And ultimately, this molecule will be ultimately finalized, and then this molecule comes for treatment. So almost 5 to 10 years will be required for a molecule to be successful and come into real clinical practice. So I'll just give you a few other examples and shorten my presentation. So I told you that cancer spreads to different parts of the body, and say if just imagine that the patient, a female patient having cancer in the breast, and we think that the nodes around this area are not involved. But to truly identify, what we can do is we can inject this molecule around the tumor. What this molecule will do is it will go around the tumor and also go around the nodes around the tumor. So we can identify the nodes by doing this image, and that particular node can be taken out by using something called gamma probe. And then this node will be surgically resected, and then it will be seen by another doctor, and who will tell whether this cancer has spread into this node. So this kind of technology is called intraoperative gamma probe. So till now, whatever scans which you are told, we'll do in the normal outpatient setup. When a patient comes to hospital, they'll just come to the department, do the scan. But this kind of analysis is done in theater. So here also we use this kind of technology. So there is another method called planning the radiation. So when a patient gets cancer, you'll be saying that they asked to take the radiation therapy. So what is radiation therapy? So basically, radiation therapy is very high energy X-rays, which are passed across the patient's body. These X-rays will damage the cells. Again, this is different from nuclear medicine. Radiation passes across the patient's body from a machine. In nuclear medicine, we inject into the body, whereas in other modalities, the X-ray come from outside the patient. But how nuclear medicine helps in this manner? Just imagine there is an organ here. This is the lower abdomen, or we call as pelvis. This is the bladder in which urine forms. There is a cancer near this organ. Suppose if we have to give radiation to this area, the radiation should go only to this area. Suppose the radiation goes to the bladder, then this area will get destroyed. So we have to limit the radiation only to the area having cancer. But by seeing this structure, I cannot decipher where this region has cancer or this region has cancer. We need some more contrast to identify the actual cancer tissue. So for that, what we can do is, again, we'll subject the patient to a PET scan. You can see the patient subject to a scanner, and an image is generated. So here in this example, you can see that there is a cancer here, just shown the PET scan, but not shown clearly in a CT scan. But by seeing this information, we can decide the radiation in such a way that very high radiation, as shown this red color, will go to this area, whereas lesser amount of radiation will go to the other areas. So in this way, the cancer is treated with the strongest radiation, whereas the normal tissue around the cancer are spared of the side effects of radiation. So nuclear medicine helps in identifying the site of disease, but it is the computer applications which help us to decide how much radiation to be given to this area. And you can see multiple curves, which is called as isocontour curves. And a computer helps in drawing these kind of curves and deciding how much radiation should be given to each areas. So this is a sequence how a scan is done. A scan will be done, and the technology will be drawing some curves like this around the cancer, and then they will be drawing the area which should receive the highest amount of cancer, and the other areas which will be having the lower. You just see the numbers, lot of numbers and tables are there. This cannot be done manually. So again, we need computer application to do this kind of approach. So with this, I have covered most of the day-to-day practice which you do in nuclear medicine and how this technology helps. In the subsequent maybe 10 or 20 slides, I will tell you what is happening actually in the computer. So which is the real domain which you are working into. So basically, filters are the programs which you know that they eliminate unnecessary information from the stored data. I told you that the rays hit the detector, they are converted into electric current. Ultimately, the electric current is processed by the image system and gives us images. When these images are processed, they will create a lot of noises. Some artifacts may be created, and we need a lot of filters to correct these problems, to give us the true high quality of images. So basically, whatever, suppose I collect all of images like this, I cannot do any processing like this in my hands. So this is spatial domain. So whatever information is in real time, which we see in our through our eyes, that is called spatial domain. We cannot do such kind of calculations. So to do those calculations, we need to convert those information into number. So that is done by converting these information into frequency. So you can see some kind of sine wave is given here. How this is done? Imagine there is a scan like this, and if you draw the profile across this, that black colored areas are like this, where you get higher amount of amplitude. White color areas, you get lesser amount of amplitude. They are evenly distributed, so you get a uniform frequency like this. Here, coming to another example. So here, the amplitude keeps on changing, and also the frequency keeps on changing. So this is converting the spatial domain into frequency domain. So this is the information in the spatial domain. The curves come like this. Ultimately, they are converted to frequency domain. I really have to accept that I don't know how they are doing this. I'm really surprised to how technology has helped us to come to this level. So what is the principle behind this? This is called Fourier transform. I think many of you would have heard about this. So basically, all the information is converted to sine or cosine form of frequency distribution, and these frequencies are handled by the machines and again they will be converted back to spatial domain. So there are different forms of Fourier transform, like discrete Fourier transform, fast Fourier transform, many other types. So what I will reiterate, what is happening is in the spatial domain, that means what we see through real eyes, we cannot do any calculation there. They are converted to frequency through Fourier transform. So in the frequency domain, any kind of calculations can be done by the computer by modeling the numbers, and then those information are given back into the spatial domain in front of us in the computer. So this is how the computers help us solve this highly technical issue. So there are many other techniques called a filtered back projection, and how these noises are corrected by the system by using different kinds of filters. Many filters are there. One of them is commonly called Butterworth filter. Basically, these filters allow certain frequencies and stop certain frequencies. It stops. Allows, this is what is done by the filter. So ultimately, there is the most advanced form of reconstruction technique. I told that all the information is the frequency, but what is the algorithm that is applied to this frequency? One of those algorithms is called iterative reconstruction. That means we got some images in numbers like 4, 5, 2, 3, and these numbers will be added together and subtracted from the previous calculation and again added together, and the system will be trying to match these calculations to the expected normal distribution. And when these two match, then it gives us an output. Why it is called as iterative is it keeps on doing a sequence of calculations, that is why called iterative reconstruction. While doing this reconstruction, it will model all the problems that could happen when an image is being acquired. So this will be too much to explain all these things, but whenever an image is done, there are many problems like attenuation, resolution, noise, scatter. So all these models will be, all these problems be modeled into that equation, and they will be sorted out such that the true information comes out and all the unwanted information goes out of the algorithm. I think you will be knowing better than this, but reason why I tell you this is how the images come to us. And ultimately we need to, as a doctor also, we need to know these things to actually understand what is happening behind the screen. So this is what a projection, that is a scan, is converted to frequency, and it is modeled into different subsets, and then it is again back projected to give us a real image. So I told you this is done sequentially, and it is there is an expected image and the image which is obtained by the system. One form of such iterative reconstruction is called maximum likelihood expectation reconstruction algorithm. So as I told, it keeps on doing continuously by modeling multiple values into that formula or algorithm. The system will take a lot of time to process it. To simplify that, another modality, another advanced algorithm came, which is called ordered subset expectation maximization algorithm. So OSEM. So what is the difference between OSEM and MLEM? In OSEM, the entire information is divided into different subsets. Suppose 100 images are coming. Those 100 images will divide into 8 subsets or 4 subsets like this. And each subset will be individually processed by the system. And ultimately, all subsets are merged together and then the information is given. This is called ordered subset expectation maximization algorithm. So this is the currently used algorithm to give all the images. And I hope many other algorithms are coming in the future. But this is, as a doctor, I understand that how computer helps us in giving those extreme clear-cut picture quality images. So this is what I have told you just now. So what is the advantage of it? Gives
Thank you. Thank you, doctor. And I think we can give some time for our participants to ask for clarifications. Shall we do that, sir?
Last slide. Just this is the image where no algorithm is conducted, and after an algorithm is conducted, you get the quality of image like this. So I just want to give some examples of journals, and this finishes my presentation. Thank you very much. I'm open to any questions.
Sir, can you show the journal list, sir, before slides, sir? Can you go?
Whenever we do any, say, research pertaining to, we will try to submit in these journals. And whenever we want any information from the physics or technology side, we will go through these journals. Maybe
Okay, fine.
you will know, but from as a doctor, I give importance to this kind of journals.
Sir, I have one doubt, sir. Sir, how you drawing the cancer cells, sir?
How we?
How, sir, if you're drawing cancer cells, no, sir. Before slide I saw how you draw that, sir. If you're using any tool, sir.
You mean drawing the cancer cell out of the patient's body or drawing in the scan?
Sir, in drawing in the scan, sir.
Let's come to that image. Something like this you are asking?
Yeah, sir.
Yeah, as I told, there are a lot of softwares which are developed by the experts. So it will, what we draw is called as region of interest, ROIs. We'll be having a pen kind of tool here. In the image, we have to draw around the image. That matrix will be recorded by the system. So suppose we draw an irregular ROI like this, it will be captured. That system will understand that only that tissue. Suppose we draw around the tonsil here, the system will keep in memory that only the tonsil has been given instruction to give the highest radiation.
What is the software, sir?
Actually, this is the software which is called as PET. This is the technology is called it PET guided radiation therapy.
Okay, sir. So if I using MRI images, I have to draw like, sir, for using I have to create new software, or the predefined software I have to take and draw the cancer cells. So it's possible. CT or MRI.
These are all predefined softwares. Obviously, you are given training to develop advanced softwares compared to this. We may be facing some restrictions. Say, just I'm giving an example. So before the scan came, they were using only the CT scans to draw this ROI. You just have to blindly draw an ROI, something like this. You can see the red color cursor which I'm following.
Okay, sir.
What would happen is this will unnecessarily radiate the brain. They will not know in which area cancer is there. But if you give an information like this, so this was possible because the computer technology made possible to fuse images from two different modalities together.
Okay.
In this way, it helped. Coming to MRI also, there are different kind of sequences. While acquiring the MR scan itself, there are different kind of sequences. And say, I will give an example. So in this image, you can see that the ROI is a different shape. It is very haphazard, right? Suppose if the system will be permitting us only to draw a square kind of ROI, it will be of no use. But the system should allow us to draw an ROI to any imaginary shape I want to.
Okay, sir.
That is how they design. Yeah.
Okay,
sir. Sir, small doubt, sir. When you use to the gamma rays in patients, sir.
Okay. Sorry. Can you please repeat?
Sir, gamma rays patient when you use to patients, sir. Gamma X-ray is used to patients, sir, but gamma rays why to use to patients, sir?
So as I told, X-ray, I think from this question, I would be able to better differentiate how this technology is useful. X-ray cannot be tagged with any molecule of interest. If an X-ray passes through the body, it will just give an image something like this. So you will not differentiate which part of the body has problem. But gamma ray is emitted by unstable nucleus. Nucleus is nothing but any atom, like sodium, potassium, or iodine, whatever. You know that iodine is in the thyroid gland. We all have thyroid gland, and we all eat iodinated salts, right? Suppose if we make the iodine unstable, inject into the patient's body, it will go only to the thyroid.
Okay, sir.
They emit gamma rays. So the purpose of using gamma rays is to specifically study one particular part of the body or one particular function in the body, which is not possible with X-rays, but possible with gamma ray or positron-based imaging in nuclear medicine.
Okay, sir. Understanding, sir. Thank you, sir.
Sir, I have a few questions. So you said we would be injecting something, right? So like fluorine 18 and then FTG.
Correct.
For the imaging, so for the molecular imaging actually. So
Correct.
is there any side effects because of these injections? or is it completely safe?
We have been told by our mentors is most of you have taken flights. Have you? Flights. When you fly through a flight in very high altitudes in the atmosphere, you are also exposed to radiation. So the same kind of radiation is being exposed in the practically used amount of activity which we give. That means the radiation which is being given to the patient is very, very less, which is not known to cause any major side effects. You need not worry about any side effects. Only when we use these radioisotopes to treat the patients. I gave an example during the last few slides that we use it for treating the patients.
For treating. Okay.
Only those radiations can have some side effects. But most of the scans, like this PET scans, gamma camera scans, literally they don't have any side effects. The patients can very well easily undergo. But for any comparative basis, you will say that MRI scan is cancer free, radiation free. These gamma scans are having radiation. That is true. But this radiation is not that high to cause any damage to the body organs. We do scans in 15 days old kids, 1 month old kids, like that.
Yeah, radiation I understood, sir, but we inject something like that. So like fluid 18, F18 and an FDG. So that is used to detecting or for the imaging purpose, so we actually inject something, right? In form of.
Correct.
So I'm asking about, is that any side effect because of that injections?
Again, it's good that you heard asked the question in this way. They are injected in nanomolar quantities. Say if you are having a fever, what is the most common tablet you take?
226.
Okay. 226 is the commercial name, paracetamol. So what is the amount of paracetamol you take? Do you know?
Amount of paracetamol?
650 milligram or 500 milligram, strength of the tablet. So it is in milligram. What we speak here is on micromoles or nanomoles. So in this kind of concentration, they don't cause any side effects, and also they are designed in such a way that they don't cause any side effects. Any molecule which is used for this. The only way a side effect that can happen is, obviously we have to use some solution to inject. That solution should be sterile. Whenever you get admitted in a hospital, they will be giving you IV fluids. They will be injecting you with glucose or saline. Suppose if they are contaminated, if you have seen a movie Vikram has acted, you can see a samurai, probably name of the samurai, in which after giving injection, the patient will develop some fever and ultimately collapses because the solution had some contaminants. We make sure that any injection we give is contaminant free. That means simply dust free. So basically, they don't cause any harm.
Okay. So next question is like, so it's a very basic one actually. So the metastasis, you were telling about the metastasis, the stage 4 cancer actually.
Yes.
So is there any way, so I don't know, so is there any way to determine where the cancer has started actually? So the root location or which organ the cancerous cell has started actually? Is there any way to determine that?
Yeah, we can tell based on the distribution of the lesions. I showed you in example. Just coming to this image, I can see only 2 focus of disease activity. Initially, they thought that this was metastasis, but now it is limited. I can now strongly say that it is seen only in the bones. Suppose if I see any other abnormality here in the lungs or in the liver, then I can have a guesswork that it could have started from the lungs or the liver. But in this case, it is seen only in the bones. That means this cancer has started only in the bones. By doing FDG scan, by seeing the pattern of distribution, we can have a guesswork. That guesswork will be 90% be right most of the time. Coming to another example, here the cancer is seen only in the lymph nodes, but not in any major organs like lung or liver. It is seen only in the nodes. So based on the distribution of the nodes, now I can say that this cancer has originated only in the nodes and not from any other organ. That is why this disease is called as lymphoma. It has originated from lymph node. So this is one way by seeing the pattern of distribution of lesions. The another way is by targeting with a specific molecule. So here I give an example. This molecule has gone and bound only to the pancreas. So that means this cancer has originated only from the pancreas. So here you can see this example. Here the lesion has started from here, and this is seen only here in the lungs. And this is a specific agent called DOTA. This is not FDG, this is called DOTA. And by specifically targeting with a particular molecule, we can say that this is the organ of origin for that cancer. So pattern of distribution, specifically radio labeling with different peptides. So both ways.
Okay, sir. So meaning is it a guess? We have some guesswork involved actually. So
Pattern of distribution guesswork is there.
okay. So is there any way to
When we specifically look at molecules, there is no guesswork. It is stated.
Okay. So the reason for asking is like,
Doctors see the patient. It's
Okay.
not a blind guess. It is a logical, medical oriented guess.
okay. The reason I asked this is like because there is a case actually like there is a cancer. It is a metastasis actually. So the cancer was it was a guesswork again, like as you said. So it was in the cervix. Then it was spread to the kidney actually. Both the kidneys got damaged because of the cancerous cell. So they couldn't able to tell where the cancer cell has started. So the origin of the origin organ actually. So that's the reason I asked. Is there any way to?
Specialty you are from?
Sir?
What specialty or what domain you are from?
No. I'm not from medical.
Just to know.
No, I'm a PhD research scholar. Sir. I'm doing my research in artificial intelligence.
So as you said, rightly point, already you have told that it has started from the cervix.
Sir, we couldn't able to find it in the sense the oncologist also couldn't able to tell where it got started actually.
But I think that kind of scenario will be less than 1% of the time. And to identify which organ the cancer has arisen from, there is another form of approach called immunohistochemistry, where we don't have any role. What they will do is they will take some sample from the tissue, they will label it with specific peptides and see in the microscope. So it is basically seeing the cells in the microscope. There they can see and paint it with different kind of molecules and which molecule targets that cell. And from that they will find out, okay, this molecule which is specific for cervix is targeting this cell. So this cancer would have developed from cervix. So this is one.
Biopsy, tissue biopsy.
Tissue biopsy followed by immunohistochemistry.
Okay.
Immunohistochemistry is specifically targeting that particular immune reactive molecule for a specific cancer.
Okay. So one question, sir. Sorry. So the SUV measurement you were telling about, no, sir. So is it only to check whether the malignancy of the cell or do we use that measurement for any other purpose?
As I told that this technology is very new over the past 10-15 years. Initially, they thought that when the SUV is more than one particular number, say 2.5 as a number, which you would have seen in many articles, they thought that if it is more than 2.5, it is cancer. It's not like that. I have told you, this is not specific. FDG can go to cancer or any inflammation, which I have shown in one of the images. So only thing which we can know is by seeing the pattern of distribution of the cells. We, as the doctors, we will know how cancer spreads in different parts of the body, how infection spreads in different parts of the body. And there are some cancers which we may not have very high SUV value. If you see the scan here the SUV values, I have not given the numbers. If you see these two images, this is appearing very light, the liver, whereas the spleen is appearing very dark. That means this is having a lower SUV value. This is having a higher SUV value. A tumor can be in either of the spectrum.
Mm-hmm.
There are different clinical scenarios where SUV would be helpful. One of them is treatment response, which I showed you here. So here you can say that if I simply say the color has come down, then the doctor may not understand. But if I say the number here was 15 and it was 3 and it is 1, then it will convey a meaning. When I give the information by numbers, then it will convey a meaning. So SUV is helpful in response assessment.
Okay, so the reason I asked this question is because in some papers actually I read it like based on the SUV value, they try to automate the detection of cancer. So they use this SUV measurement for actually to detect whether it's a malignant or benign.
For any person, they will be strongly believing something which may be right or may be proven wrong at some point of time. As an expert, I say that SUV value cannot be used for any such kind of analysis. Just to do some research, they are trying this tool. but we are the end users, right?
Yes.
We know why, in what way, but maybe if any of you are interested in any research question to be developed, you can definitely contact me. I will be happy to help you. Suppose if you come with a research question, I can tell you whether that question has some logical meaning, whether that could be pursued. But SUV, I think is not the right modality, right kind of approach.
Okay. So one final question actually. So we are not the experts actually. We know how to do things in the computer actually. So we write algorithms, but you are the end users and you are the actual experts actually. As an expert, do you have any suggestions or ideas so that can be used in the computer vision research project that could help you in a different way actually? Like you said, right? So these work being started very long actually. So after the introduction to computer and computer vision, so it helped you a lot in a different way. So likewise, so do you have any suggestions or an idea that could be, because we are all, most of people here are researchers actually. So people are doing researches in AI and oncology, cancer images, medical imaging. So do you have any kind of ideas or suggestions that could be implanted in our research work?
AI is artificial intelligence. I think I'm right about the abbreviation.
Yes, sir.
In artificial intelligence, there are two ways. One is artificial intelligence of processing the data, and another is artificial intelligence in interpreting the data. We actually do interpretation. You have done both process. You have written the programs for processing as well as interpretation, but the end users take some clue from the interpretation softwares and we do manual interpreting. Artificial intelligence in interpretation will take a long time to come to clinical use. You would have seen that these days they try to, you would have even seen the interview of Sundar Pichai that they are trying to implement artificial intelligence in detecting the changes in eyes. What they say is they can take a picture. If you wear the spectacle, it will take a picture of your eyes and will give some information. But it can never come to reality because there are hundreds of logical parameters which cannot be modeled. The exact example I can say, I'm not giving a negative feedback. I'm just saying that there are some artificial intelligence which can probably never be arrived at. I may be wrong in the future. For example, take ECG by the Apple Watch. Apple Watch gives you ECG, right?
Yes.
So it just will give you only whether there's a change in the pattern of ECG. But there are thousands or billions of diagnoses can be made by ECG by the cardiologist by seeing the proper conventional ECG. But that can never be automated. So in such a way, what I would suggest is artificial intelligence can be used for developing processing based applications, not for interpretation. I think I have given some idea of how artificial intelligence can be developed. So whatever is done by the processing system is artificial intelligence only. Anything we think that artificial intelligence means only interpretation side. I am just focusing more over the processing side, development side before interpretation. Maybe if you sit together with me personally or any other doctor, that will be a more meaningful way to discuss what you have in mind, whether that is right or wrong in that way.
Yeah, thank you, Doctor. I completely in line with you actually. So I always believe in that human intelligence cannot be replaced with a computer-based computer vision intelligence actually. Yeah. But the reason why I asked is people started research work on AI in the sense they try to automate things actually. It's like how it can help the clinical research or the clinical findings actually. That's the reason I asked, is there any way which actually we can focus on something? So because people start, most of the research work or focuses on classifying the images actually. So instead of that, so if we can focus on or if we can shift the focus to some other way or some other area which you experts are seeing it as a pain area, we can focus on that. So that's the reason I asked this question.
We become experts only as medical experts, but the real experts are the computer engineers. As I said, though the concept was there, only after the advent of computer, everything had been done. But the thing is, everything they are done in sequences. One information is layered over the existing information, and these are all done by the industry experts. Most of the researchers in the current world don't happen in the universities. I think many will agree. The universities obviously breed the research minds, but lot of technologies have come and they are in the market. if you see Tesla was not developed in the university. So Tesla was developed in the market. So there is an existing technology. You will be going there and working in the technology, and there you will get the information. Okay, if I add one more layer in this form of okay, this algorithm is having some features, I will do something to do this. This is how I think AI will slowly develop. We cannot directly suddenly open a new avenue, but I can always help. That's not an issue.
Yeah, okay. Thank you, Doctor. Thank you for your time. Thank you.
Thank you, sir, for sharing your precious ideas to the audience. I'm sure that they enjoyed the session and got more knowledge on nanotechnology and nanoparticles for vivo imaging. So thank you once again, sir. No duty is more urgent than that of giving thanks. Now I would like to call upon Creative Sparkle Dr. B. Lavanya ma'am, Principal Investigator, for vote of thanks.
Good evening, all. I take the privilege of rendering the vote of thanks on the first day of MHRD RUSA 2.0 sponsored 2 weeks workshop on analytical tools for image processing. Let me thank the Almighty for His grace on us during this period and for blessing us to continue our academic and research activities. I thank the authorities of University of Madras, Professor Dr. S. Gauri, Vice Chancellor, Professor Dr. N. Madhivanan, Registrar and RUSA 2.0 Coordinator, for his support in conduct of this workshop. I also thank our dynamic group leader, Professor Dr. S. Balakumar, Director, National Center for Nanoscience and Technology, for his continuous encouragement and unceasing support for initialization of this project and continuous support till date. I thank Dr. A. Santosh, today's resource person, for his informative and useful knowledge sharing. It was indeed very useful, sir. Thank you. I thank the fellow participants, research scholars, and students from various universities, colleges, and research institutes pan-India. I thank our professors, Dr. P. Thangavel and Professor S. Gopinathan, for their support. I thank the conveners of this workshop, Professor Dr. Chitra and Professor M. Swarnam, for their untiring work for conduct of this workshop. Thank you all. We, the conveners of this workshop, expect the same support from all participants throughout the workshop on all 15 days. As mentioned already, it is definitely going to enrich your knowledge on most wanted hot research topics, analytical tools for image processing. Thanks to this pandemic, we are fortunate to get the knowledge sharing from eminent resource persons both nationally and internationally. So participants, do not miss even a single session. Thank you once again for your patient listening. Meet you all tomorrow at 4 p.m. for a session on Comprehensive Cancer Care through Biomedical Imaging by Dr. D. Peter Augustine, Department of Science, School of Science, Bangalore University. Thank you all.
Thank you.
Thank you, ma'am.
Thank you, Doctor, for your wonderful informative session, and it is highly interesting. Dr. Santosh, and most of the students are focusing on medical imaging now. I think this will help. This session is more informative, and I think this will give a clear vision about how to proceed. As we have discussed artificial intelligence, then parameters like SUV, how to proceed. If any students are having any doubts, kindly clear our doubts, sir. Thank you so much for your interactive, very informative session, and a very much valuable time you have spent with us. Thank you so much.
I could see some chats, but not able to reply. Points, but,
yeah, sir.
My number could
we can give them answers.
Push me and I can help them.
Thank you so much, sir, for your valuable time with us. And it is more informative to all young researchers and university faculty members like us. Thank you so much.
It's a great 2 weeks ahead for you. Thank you.
Thank you, ma'am. A good event never ends in the world. They take only a pause and keep us waiting for the next. Let us meet tomorrow, an effective day to session. Thank you, guys. Kindly fill the feedback form and leave the session.
So thank you one and all present here, and we have our feedback session. I think you can wait for another 5 minutes. Then we will leave the meeting. Okay.